So the uniform distribution on the Cantor set is formed by taking the interval 0, 1 and successively removing the open middle third of each of the remaining intervals. So let's call a random variable x to be a uniform distribution on the Cantor set. We want to compute the variance of x. So if we draw out the Cantor set, we start off with the interval 0 to 1, as seen below. And then we proceed to remove all the middle thirds of the interval. So with this distribution right here, we see that the probability that this random variable lies within the interval 0 to 1 would just equal 1. But then when we proceed in removing all the middle thirds of these intervals, we can try to get some intuition of how to actually solve this problem. Oops. So now we have the interval 1/3 here, which has been removed from the set. And therefore we have the probability that this random variable x lies in the interval 0 to 1/3 to also equal the probability that x lies in the interval 2/3 to 1 to also equal 1/2. And then we can proceed with this kind of partitioning, or removal in a similar way. So this is from 0 to 1/9. This is 2/9 to 3/9. This is from 6/9 to 7/9. And then 8/9 to 1. And we see that the probability in lying in each one of these intervals here is going to be 1/4. Probability. Now we know that the Cantor set will continuously keep on removing these intervals and that the Lebesgue measure of the Cantor set will be 0. So this distribution is an example of a singular distribution where the Lebesgue measure is 0, but we still define a probability measure over this set of Lebesgue measure. And it might seem kind of difficult to actually just try to even imagine how you can define this kind of random variable on the set, let alone finding some properties of the distribution, such as the expected value and the variance, for example. But we can nevertheless solve this problem by considering some kind of decomposition of the set, because recall that the Cantor set can be defined as a set partitioning this way. Which I'm shamelessly looking off from the Wikipedia page next to me. So basically, each iteration in this sequence then takes away the middle third of each one of the remaining intervals. If we were to equate that in the probabilistic sense, then we can actually have that x, the random variable x defining the uniform distribution around the Cantor set, is actually equal in distribution to y, which I'll define in one moment, where y follows a Bernoulli, a coin flip, with probably 1/2. So the reason why is because, once again, by the properties of this distribution, we kind of have this recursive definition where x, this definition of a Cantor distribution, must satisfy that all the middle thirds are missing. So we either first take the middle thirds that lie left of what we currently have, or right where we currently have, which is denoted by the y and 1 minus y in the Bernoulli distribution here. With this representation, we can then actually compute some quantities and then solve for the moments without actually having to compute from the definition of the expected value. So for example, if I take this expression here, which I'll call the star expression. So taking the expected value of the star expression on both sides, we find the expected value of x equals the expected value on the left-hand side. On the right-hand side, I mean. And since y and x are independent, so I've got to define that earlier, but y and x are independent, we can then pass the expectations through. And since y is Bernoulli with parameter 1/2, these all come to 1/2. So simplifying some expressions, we have expected value of x divided by 6 plus 1/2 here, so get 1/3 plus expected value of x divided by 6. Then we collect terms and subtract both sides from these terms. We get that 6, 1/3, so 2/3 expected value of x then equals 1/3, which then gives us that expected value of x equals 1/2. Now, if anything, we might actually have been able to guess that expected value of this Cantor distribution would have been 1/2 actually, so because even though we're moving the middle thirds, the distribution remains symmetric all the way throughout. So the balancing on the lower half matches the balancing on the upper half from this diagram we see here. And then here, when we keep on moving middle halves, all the balance of weights in the lower halves equal the balance of weights in the other half. So presumably, it makes sense the expected value should equal 1/2. Now, the difficult part is computing the variance, but that's not that much harder to do now that we know the strategy in using the representation given by the star expression. So continuing with this kind of laboring, we now want to compute the expected value squared. So again, taking the star expression we see right here and squaring both sides, we now proceed to compute the expected value. So we now have the expected value of x squared to now equal the expected value of this entire giant expression squared. Which through a sheer amount of just algebra and expanding, which I'll skip the steps here, we can get this expression we see here. Sorry about that. I'm gonna make this e here a little bit smaller. And then seeing how the expected value of x appears on both sides of this, and of course expanding the expected value of 2 plus x squared, we can get that the expected value of x squared equals 3/8. So combining this together, so therefore, the variance of x equaling expected value of x quantity squared, x squared quantity squared minus the expected value of x squared just equals 3/8 minus 1/2 squared, which equals 1/8. So I guess the moral of this problem is the fact that we don't necessarily use the standard definition of expected value, the integral of x times d mu, the measure over the set, because trying to do so would actually lead to, it'd be fruitless, right? So, but you rather using representation and then computing the quantities that appear out of the representation, we actually come up with a pretty slick solution computing the variance. Thank you for listening.